recording, and let's see, here we go. So we are in week 10, y'all. So today, hello. So today what we're gonna do, y'all, we're gonna finish up 4.7 and we're gonna do 4.8. And y'all, I'm gonna do it just like we did the other day. I'm gonna have two videos, so we'll finish up 4.7 and then I'll stop recording. We'll take like a little 10-minute break and we'll come back and do 4.8, all right? So let's see. Let me get my notes ready. Here they are. And so y'all, when we were here the last time, this was the last problem we had done out of 4.7. So we're going to pick up where we left off. Okay. So let me see. Let me get my pen going on here. And there we go. Okay. So this problem here, y'all, says we have a box with no top is made from a rectangle with dimensions A equals 14 by B equals 10 inches. By cutting a side X at each corner and turning up the sides. Determine the value of X that results in a box with a maximum volume. Okay, so let's take a look here, y'all. They got it. We have this square, and what we're doing is we're cutting the little square corners here. Okay, so we're going to cut those little square corners so that we can now make a box. Okay, so y'all, one thing I want to emphasize here is they're giving me the dimensions. Okay. So A, which is the distance from here to here, is actually 14, and B, which is the distance from here to here, is actually 10, okay? So we're going to cut out these little boxes that are going to have sides of X, okay? So what I'd like for us to think about now is, what would the distance, say, from here to here be? Yeah, that'd be 14 minus 2x, right? Because didn't we cut out that x and didn't we cut out that x? So now this little distance right here, y'all, in this little distance, how are you doing, Matthias? This little distance right here is going to be 14 minus 2x. Now, I've got another question for y'all. Let's see. What would, say, this distance right here be? If the total distance from here, y'all, was 10, what would that green distance right there be? Anybody know? Yeah, it'd be the same thing, right? It would now be 10 minus 2x, okay? Because again, we're cutting out this little x right here and that little x right there. So, y'all, an artist I am not, but I'm going to try to draw the box that we're forming. I want you to think about what we're doing. We're going to fold, like we're going to make a little crease right here. We're going to make a little crease right here, a little crease right here, and a little crease right here, so that we can, if you think about it, we can fold up those edges, right? So wouldn't my box now look, that's horrible already. All right, let's see. Wouldn't my box now look, there we go, that's not too bad. Wouldn't my box now look something like that? Where, there we go, where this side up here is 14 minus 2x, and this side here is 10 minus 2x, and that little side there is x. Does that make sense in what we're doing? Okay, so look, there's the shape of our box, right? There's our box. All right, so I wanted to draw that picture because, yo, especially with application problems, pictures are like really helpful, okay? So this problem here, the good thing about this problem, y'all, they really walk us through the steps. So before I even, did anything else, I just kind of wanted to draw the picture of what the box was going to look like. So first off, it says express the volume V as a function of x. Okay, so remember the way we find the volume, y'all? It's the length times the width times the height, right? Okay, so the length, I don't know, I'm going to call it 10 minus 2x. The width, I'm going to call it 14 minus 2x. And the height, we're going to call that x, right? Because we have this side, and that side right there, okay? So right in here, y'all, that's what I'm going to write here. Okay, that's going to be my volume. All right. Now, the second part, part 2, is saying, can we find the domain of the function of x? So we want to find the domain. Now, think about this, y'all. If I come back to this original picture that I had here, right? Let me clean this up a little bit. Clean, clean, clean. Okay. We already said that the distance from there to there was 14, and the distance from here to here was 10. So the domain, what we're thinking about in terms of the domain, y'all, is how big of a little x can we cut? You know what I mean? Like, we can't cut more than a certain amount, right? I couldn't make my squares, look something like that, right? Because then I have like this really kind of tall, narrow box, right? And then there's going to be a limit. So I want you to think about that limit for a minute. Remember, this is the length, this is the width, this is the height, right? Okay, so first off, because we're cutting little boxes here, do you agree with me that number one, x has to be positive? So I'm actually, in order for me to cut something, it's got to be a positive number, right? I got to cut at least something. So this part we know for sure. Now, the other thing is we're going to look at these numbers. These numbers also have to be positive, y'all. So 10 minus 2x needs to be positive. So does 14 minus 2x, okay? Because we're dealing with like measurements, right? We're dealing with length and width and height, and the length, width, and height of a box, they all have to be positive numbers, right? It can't be negative, and it can't be zero. I can't have a box with a length of 0, then I don't have a box anymore, right? Okay, so look, let's go ahead and solve this inequality right here, y'all. If I solve that inequality, I'm going to have 2x is bigger than negative 10, and it's probably been a minute since any of us have dealt with inequalities, but we're going to go ahead and divide both sides by negative 2. And if you remember this, great. If not, I'm going to show you right now. When we divide by a negative in an inequality, y'all, the sign of my inequality is going to reverse. So I know it said greater than 0 because it needed to be positive, but if we divide by a negative number, then the direction of my inequality sign flips, okay? Let's do the same thing for this one right here. So yeah, we're gonna keep going here. Let's do this one, and then we'll talk about that in a second. So when I move the 14 over, it becomes a negative 14, right? We're gonna go ahead and divide both sides by negative 2, and I'm gonna come up with x is smaller than what number? 7, right? All right. I want you to think about a number line for a second, y'all. Here's my number line, okay? I'm going to put 3 numbers on that number line. The 3 numbers I'm going to put are 0, I'm going to put 5, and I'm going to put 7, okay? Now, let's do it like this. The way we can find the domain, x needs to be bigger than 0. So bigger than 0 means put an open circle here and shade everything to the right, right? Now, x also has to be smaller than 5. So put an open circle right here and shade everything to the left, okay? And we're going to do this a third time. X has to be smaller than 7. So put an open circle right here and shade everything again to the left. What we're really looking for here, y'all, is where did we have the overlap? You know what I mean? Where did we shade every single time we did that shading? Does anybody know just by looking at the picture? Between 0 and 5. There we go. Perfect. So my domain, y'all, is going to be the open interval between 0 and 5. It needs to be positive. That's why it's bigger than 0, but it has to be smaller than 5. Okay? So now look, I'm going to come back over here. And this piece right here, y'all, is telling me that my domain needs to be between 0 and 5. I want to explain something real quick, y'all. In terms of my domain, I mean, I wanted to walk y'all through the process so that you could kind of get a visualization of what's happening. But think about it this way. Do you remember when we set up our sides? And I'm just going to kind of clean this up a little bit. Let's see. There we go. Okay, we said this side here was 14 minus 2x, and we said this side here was 10 minus 2x. If x was the number 5, 10 minus 10 would be what? 0. Okay, so that's why it has to be smaller than 5. You see what I mean? And I know we had that. Well, what about 7? Well, if we plugged in, if we took a number, say, just smaller than 7, or 7 itself, 14 minus 14 would be 0. But if I were to plug the 7 in here, then it would be too big, right? And my sides have to have actual positive lengths, right? So that's why we're doing what we're doing. All right. Step number 3 says, can we find the derivative of b? Can we find b prime? And I know the answer is yes, we can do that. I want you to think about this for a second, y'all. Remember how we did in part A? This is what we wrote out. Yeah, let's go ahead and multiply this whole thing out, right? Okay, so I'm just going to FOIL this out. So 10 times 14 should give me 140. 10 times a negative 2x should give me a minus 20x. That's going to give me a minus 28x. And negative 2x and a negative 2x is going to give me a positive 4x squared. I still have that x in front of it, though. Okay. So let's see. This is going to be 140. If I combine those two, that should give me a minus 48x and a plus 4x squared. Okay. And now all we need to do is distribute the what? Just distribute the x, right? So everyone agree 140x minus 48x squared plus 4x to the third? That's what our volume is. So all we did is just multiply it out, right? Okay, so guys, obviously the reason we wanted to do that is because we want to find the derivative. And now that we have a polynomial that's already, right, expressed out, we can find the derivative hopefully pretty easily. What's the derivative of 140x? 140, right? Makes it easy to do. What about the derivative of a minus 48x squared? I'll give you a hint, it's going to be a minus. Yes, I'm sorry, say it again. Right, but this, what's the derivative of this one?
148, 132,
96. Okay. And then what's the derivative of 4x to the third? 12x squared. There you go. Perfect. Okay. So we found the derivative, right? 140x minus 96, 140, sorry, minus 96x plus 12x squared. Okay. So we got that part. Now look at step number 4, y'all. Step number 4 says, can we find the critical points in the domain of x? So remember, the way we're going to find the critical points is we're going to take our derivative. Yeah, we're going to set it equal to 0, and we're going to solve for x. So let's see. I want to see if I can divide, just to make these numbers a little bit smaller. So let's see. I don't think 12 goes into, yeah, I don't know if 12 goes into all of them. So 96, can I divide it by 12? 8, yeah, that one goes in nice and easy. What about, not by 140? Yeah, so that's not going to work. Okay. All right, so let's try this. Let's try dividing them all by 4. Right? So if we divide them all by 4, that's going to give me a 3x squared. Let's see, 96 divided by 4 was, I'm sorry, 24, very good. What about 140 divided by 4? 35, okay, perfect. All right, oops, I forgot my x right here. Okay, so guys, I'm going to tell you right now, this problem here is not going to factor out nice and pretty, okay? Because it doesn't factor out nice and pretty, we're going to go ahead and use the quadratic formula, okay? By the way, I'm just curious. Does anybody know, is there a way to solve the quadratic equation on your graphing calculator? Anybody know? I'm just curious.
I can do it on mine.
Yeah, but what do you use?
It's literally a function called zero. Or there's another one called polygon.
Okay, my question is, where did you find it? Did you go to catalog or something? Like on your calculator, what are you doing?
On me?
Yes.
There's
Is there a particular button you're pressing right away?
yeah, it brings up I would try catalog.
Okay, let's go catalog. I'm just curious if it'll do it.
See, and then you have to look at the function.
What function am I looking for again?
Quadratic, like bar maybe or column or zero. I have a feeling it's good because it's a graphic.
Yeah, I'm just curious if it does it. I mean, I mean, guys, we can use the quadratic formula. It's not hard to do.
It's just faster.
Yeah, it's just saving some time.
So columns, so you use the column. Column method.
Yeah.
It might be. I have both functions. I don't know what the difference is. You know, I haven't.
Yeah, I may not have it on this one. This is an older calculator, y'all. This is an 83 plus. I don't even know what year this came out. But the funny thing is that I used to have a calculator when I was in college, which was a long time ago. Yeah, see, it wouldn't be there because it's alphabetical order. You know what I mean? Okay. So I used to have it on another calculator that I had, y'all, which was something called the TI-85. I don't even think they make it anymore. But it was a way to, it was like an equation solver, and it was on here, and I just don't know where it is. But I'll look it up later. I didn't think about looking it up beforehand, but I'll look it up later, and if I can find it on here, y'all, if it's on the 83 plus, it's going to be on your 83 or 84. But anyway, it's not really important. Let's go ahead and just use the quadratic formula. So look,
Yeah, you have to throw it as a thing.
yeah,
You can make your own.
yeah, I know I can make one, but my laptop is a little funky. So let's see. Okay, so I'm going to go ahead and do it here. So look, negative b, if b is negative 24, negative b is going to be positive 24. Let's see, negative 24 squared minus 4 times a times c all over 2 times a. Okay, so 24 plus or minus, let me do this. What's 24 when I just, what's 24 squared? 576 minus whatever 4 times 3 times 35 is, 420 over 6, 24 plus or minus square root of, let's see, 576 minus 420, 156, all over 6. Okay, now at this step, y'all, I am going to use my calculator to get my two answers, okay? I'm going to do it. So look, this is what I'm going to do. I'm going to say, look, what is the square root of 156? Oh, I don't know, 12.4 and change. Let me add 24 to that, and then let me divide it by 6. And I'm coming up with, guys, I'm going to go ahead and go to 4 decimal places. Y'all agree 6.082?
Yeah.
Okay, 6.082, that's actually 3 decimal places. So, okay, I'm going to go to 3 decimal places. Already did. All right, let's do the second one. So let's see. What's the square root of 156? Okay, so now I have to do 24 minus that answer and divide that by 6. And I'm coming up with 1.918, right? So these are the two numbers that I'm coming up with. Yo, if I'm using the quadratic formula, like I said, if it doesn't factor, you're going to get decimal answers, right? If we, I mean, it doesn't mean you wouldn't get decimal answers if it's a factor. It just means that the decimals are going to be terminating decimals, or usually pretty decimals. But yeah, we don't have that here, right? So those are the two numbers that we end up with. Now, I'm going to scroll back over here and look at the question for number 4. Remember the two numbers we came up with? One of them was 1.918, and the other one was 6.082. So 1.918 918 and 6.082. Look at the directions on problem number 4. Problem number 4 says, find the critical points where in the domain. You remember what our domain was? We wanted numbers between 0 and what? 0 and 5. So which number would I use? Well, they're both positive, right? But I would use the 1.918, right? Because that's the number that's between 0 and 5. Okay, now, y'all, I'm going to be real honest with you. I think the way they worded this problem, at least for parts 5 and 6, are a little funky. Because it says, what's the value of v at the left endpoint? So what they're referring to is this endpoint, and the value of v at that endpoint. Oh, I'm sorry, never mind. I was mistaken. I was thinking of the derivative. Yeah. So what we're going to do now is we're going to come back over here, and we're going to plug in 1.918 into our polynomial. So I'm going to plug that in right over here. Hello. So look, y'all, remember when we did or right here, either way, it's the same polynomial. I'm going to plug in my volume of, or the value of v right in here. Okay. So let's try that. Let me grab my calculator. So it's 10 minus 2 times 918? Okay, like this. And then 14 minus 2 times 1.918. And close that off. And then another 1.918. Okay. And yes, ma'am, go ahead. Okay. Yeah, so remember, so look at the directions for, let me scroll up here. Look at the directions for part 5. It says, what's the value of the volume at the left endpoint? So if we were to take this number here and plug it into my original volume equation, which was this one right here. So all I'm doing is I'm plugging into 1.918. So I want to show you what I did. Look, I have 10 minus 2 times 1.198, right? And then 14 minus 2 times 1.918, and then times the other 1.918, right? So if I hit enter right there, the number that I'm coming up with is about 120.164 is the value that I'm coming up with, right? So right here, y'all, I'm going to put 120.164. Okay, now, y'all, we're going to do the same process again, but now we're going to plug in what number? 6.082, right? Okay, so look, y'all, we're going to do the same process we did before. If you want to, y'all, on your calculator, you can do second entry, and it just enters exactly what you typed in before. And all I'm going to do is change that 1.918 to a 6.082, right? So let's go 6.082, and I'll change it over here as well, 6.082, and then I'll change it one last time right here, 6.082, right there, and I'll hit enter, and look at the number I'm coming up with here. What kind of number did we get? Negative. You know why we got a negative? Because that 6.082 was not in the domain, right? So right here, y'all, I'm going to put a negative 24.164, okay? Now, what is the maximum volume? The maximum volume was when we plugged in the first endpoint, right? Which happened to be 120.164. And the value of x that we used was 1.918. Does that make sense? And how we're able to go about that? So, you know, we knew, so let's put it this way, y'all. In doing this part right here, Number 6, this one was, I knew it was going to give me a number that was off because that number that we plugged in was not even in the domain. Does that make sense? But it's just kind of showing me that, look, I know I got 2 critical values, and if we plug them both in, what's going to happen? But because that second value was not in the domain, it wouldn't make sense to say the maximum volume was a negative number, right? Volume is going to have to be a positive number or 0 if I don't actually have a box. Yes, ma'am. We don't put in both because, very good. So guys, Jennifer's question is on number 4. The only reason we're putting in the 1.918 is because of this part right here, because it says it's in the domain, right? So because my domain was from 0 to 5, I really only wanted to use that number there. Good question. Yeah, that's really good that you caught that. Glad you brought that up. Guys, let me ask you a question. How do you feel about these volume problems? I mean, did it make sense in how we drew our picture? Like, let me zoom out a little bit. On what part? On plugging in the number here? Like in doing the quadratic formula? Yeah. So again, if you can do it on your calculator, y'all go ahead. During the break, I'll Google how do you solve, how do you do the equation solver like on a TI? I'll do it during the break. I'm sure there's a way to do it. Like I said, I'm guessing y'all, again, back in 1995, when you guys may not even been around, and I had this old graphing calculator called the TI-85. It had an equation solver on there, so it was easy for me to do. I'm guessing it has to be on the 83 too, because it's funky the way they do their numbers, right? But the 85 actually came out first.
Yeah, but you know, like the 85 was the Empire back in 1990, whatever.
Uh-huh.
Like, and 83 is very much like a post-system technical for that. Even though this feature was on a calculator like 20 years ago, we're not going to give it to the new calculator because it's a cheaper model, like not the
Oh,
line.
yeah.
That might be a thing.
Maybe. It's possible. Yeah, it's possible. So that's doing the regression for a quadratic equation. So if you have like in stats, we have like scatter plots. You have a bunch of points, and if the points kind of follow a quadratic model, you basically use a thing, and it'll tell you, okay, this is the quadratic, this is the graph of the quadratic equation that kind of best fits that model. It won't be exact, but that's what that's for. But yeah, I'll look something up, guys, during the break. I'm sure if we just do a simple Google search, hopefully we can find something. The other thing is, y'all, with these calculators, and again, I don't know how much you guys are familiar with this stuff here, but with these calculators, you can actually do programs. You can actually write a program and how to do it, stuff like that. So like when I taught stats before, y'all, on the 84 calculator, and I don't know if anybody has an 84 here, but on the 84, there's a certain function that was available on the 84 and it was not available on the 83. And so I just like Googled it. There was a simple program. I mean, it was honestly like 8 lines. And so what I did in my stats class was everybody who had the 83, I used to have a class like 5 or 6 84s. And I would say, hey, look, give me your 83. I'm going to give you this 84. And the next time we come back, I'll type in that program and then I'll give you back your 83. So I did that for everybody. For whatever reason, on my computer, when I type in like a program, and then I don't even have to turn off my computer. Even if it just goes to sleep, the program would erase. So on this one here, like every single time I had stats, I had to type in that thing, and it was a pain in the butt. You know what I mean? So I didn't want to mess with it anymore, and I don't know why my 84 app wasn't working, but that's what I'm using now. Yeah, something like that. Okay, so look, y'all, we got another problem. This is very similar to the first problem that we did on Monday. And look what it says. A box with a square base and an open top must have a volume of 219,488 cubic centimeters. We want to find the dimensions of the box that'll minimize the amount of material used. Remember what I told y'all? In these problems here, we are, because they're optimization problems, we're either maximizing or we're minimizing, right? So in the problem that we did before, we were trying to figure out what size of little squares do we need to cut so that we could maximize the volume, right? In this problem that we're doing here, we want to find the dimensions of the box that are going to minimize the amount of material used. So first thing it tells me, we have a box with a square base. So the base is going to look something roughly like that, right? There's the base. The height of the box, I have no idea how high it's going to be, but it's going to look something roughly like that. And remember, the top is open, right? So it's an open top. Let's call this height, let's call that height y, okay? So again, first thing here, y'all, the volume of a box is going to be the length times the width times the height. So that should give me x squared and y, right? If I'm doing the length and the width and the height. Okay, the second thing is, they already told me what the volume is supposed to be. We were told that the volume was supposed to be 219,488. So that means the volume, x squared y, is supposed to be equal to 219,488. What I'd like for us to do here, y'all, is I'd like for us to solve this equation for the letter y, meaning I want to get the letter y by itself. So wouldn't it just be 219,488 over an x squared? Okay. The reason I was doing that is when I read the problem right here, it says, first, find the formula for the surface area of the box in terms of only x, okay? So let's see. Let's see if we can find a formula for the surface area. So the surface area, we have the square base. So the area of that base, everybody agree that's going to be x squared? Okay, and then we have all the sides. So what's the area, say, of this side? X times y, right? But we have 4 of those sides, right? Because we have that side here, we have this side here, we have this side here, and that one back there, right? So we have actually 4. Now it says, let's find a formula for the surface area only in terms of x. All we're going to do now, y'all, yeah, we're just going to do a direct substitution. So I'm going to go 4x, but right here, I'm going to use that as my new value of y. So that was a 219,488 over an x squared, okay? All right. So first thing I'm going to do, y'all, is what's 4 times 219,488? I don't know, but we'll figure it out right now. 219,488, we said times 4, and I'm coming up with 877,952. So 877,952. Question, y'all, do you agree that this x here is going to cancel with one of those down there? Okay. All right. So for part A right here, y'all, it's telling me, can we find a formula for the surface area? We just did. This is going to be x squared plus 877,952 all over x. Okay. Look at step number 2, or part B, whatever you want to call it. Now it says, can we find the derivative of that function? And I guarantee you we probably can. Y'all, before I do the derivative, can I write this so that it looks like that? So that I can now use my power rule and stuff like this, right? Okay, let's find the derivative. So the surface area derivative, what's the derivative of x squared? 2x. What about the derivative of this piece here? Negative 877,952. What would be the power? X to the negative 2. Guys, can I write it on the bottom with just an x squared? Okay. I know it would be x to the negative 2, but I'm going to write it like this. You can write it either way you want, okay? Not a big deal. Okay, so that's what I'm going to enter in right over here. So right here, y'all, I'm going to put a 2x minus 877, 952 all over x squared. All right. Then we have part C. Part C says, now calculate when the derivative is equal to 0. That is when a prime of x is equal to 0. Here was our a prime of x, right? I use SA for surface area, but whatever. We're going to find when that value is equal to 0. So look, if I set this thing here, y'all, equal to 0, when I move this guy over that way, it becomes a positive 877, 952 over x squared. I can think about that 2x as 2x over 1, and now we can just cross multiply. So 2x times x squared gives me a 2x to the third. 1 times 877, 952 is still 877, 952. Right? How do we get rid of the 2? Divide it by 2. So let's divide that number by 2. Okay. And I'm coming up with 438,976. 438,976. Okay. Next question. Anybody know how do I get rid of the x to the third? Cube root, right? Good. Okay, so those are going to cancel, and I'm going to write my answer over here because I'm kind of running out of room, y'all. So let's see. Guys, y'all remember how to do that in the calculator? How do you do your cube root? Anybody remember what power it is? 1/3. Good. So guys, when it's the cube root, the exponent is the 1/3. Let me just write that down real quick because I'm not sure how much, I'm not sure how much you guys remember about how to do these kind of things. But think about it this way. When you have the cubic root of x, it's the same thing as x to the 1/3. So if you have the fifth root of x, it would be x to what power? 1/5, right? Okay, I got a tricky one for you. What about the cubic root of x squared? Anybody know? X to the 2/3. Okay. Okay. Just to make sure that you guys know. Okay. Like guys, I'm not going to test you on that or anything like that. But I just want to make sure that if in case you ran across a problem like that, whether it be today or whenever you take Cal 2 or whatever it is, you kind of have remembered. And again, in some of the classes, y'all, we talk about it briefly, but then it's like we never really talk about it again until 3 semesters later. And it's like, you remember when we did 3 semesters ago? I'm like, man, I don't remember what I did yesterday, Okay, so let's do this with our calculator. Let's do the x to the 1/3. So we're going to take our answer and we're going to raise it to the power 1/3. And hopefully we come up with a nice, pretty number. Hey, very nice, right? 76. Man, we couldn't get a prettier number than that. Okay. Now, I'm sorry, I just didn't hear you. So when it's cube root, yeah, when it's the only time you're going to do like plus or minus is if you have an even root. So if you have like square root, fourth root, sixth root, eighth root, then you have to worry about plus or minus. If you have an odd root, you don't have to worry about plus or minus. It's just the answer that you come up with. Hold on, we'll come back to a second. So look, y'all, we came up with x equals 76. Now, technically, we are done with the problem because we have answered the 3 parts that it asked me to answer, right? And because this is supposed to be a minimum, the way we could verify, y'all, that this is a minimum, I mean, I'm going to show you how to do it, but again, in terms of the problem, we have answered parts A, B, and C. You know what I mean? So technically, we've actually done the problem. But to verify it's a minimum, what we could do is if this was the first derivative right here, we could find the second derivative. So let me do this. I'm going to erase this business. So I hope that made sense, but I'm just going to clean this up a little bit. Yeah, let's find the second derivative. So let me see. Of the original function, the function that we had. So the first derivative ended up being 2x minus 877,952. I'm going to put it with an x to the power negative 2 since we want to find our derivative. So if we were to find the second derivative, y'all agree that'd be a 2. And then this is going to be a plus 877,952 times 2 is like 175,5904 over x to what power now? X to the 3 on the bottom, right? Right. Okay, now look, y'all. The way we would verify that this is actually giving us a minimum is we're going to find S double prime of the critical value, which came out to be 76. I want you to think about this for a minute. Number one, is this number positive? Yeah. This number obviously is positive as well, right? If I plug in 76 and I raise it to the third, would that also be positive? Yes. So a positive number plus another positive number is still going to be what? Positive, isn't it? What I'm really looking for here, y'all, is the sign. Remember, if the second derivative at that value is positive, then it's telling me that that value happens to be a minimum of the function, right? So do I necessarily need to know what the number is? No, I just need to know whether the number is positive or negative, right? And again, if you think about this for a minute, again, we already know that's positive. And when I plug in 76 there, that's going to be positive. And a positive divided another positive is still positive. Adding 2, it's still going to be positive, right? So that's really all I was interested in doing. Does that make sense? Okay, but again, we had technically already solved the problem because of the questions that it asked me to find, right? It really only asked me to find those 3 things without really verifying that it happened to be a minimum, but that's how I would verify it. You understand my point? Okay, so I wanted to go through that just because did I answer the questions that it asked me? Yes, I did, but did I really verify that it was a minimum? I actually did, right?
So,
Are we good? Okay. So look, y'all, we got one last problem here, and then we'll take a little breather, and we'll come back and do, what is it, 4.8. Okay, so it says a cylinder-shaped can needs to be constructed to hold 550 cubic centimeters of soup. The material for the sides of the can cost 0.4 cents per square centimeter, and the material for the top and the bottom of the can need to be thicker, and they cost 0.05 cents per square centimeter. Find the dimensions for the can that will minimize the production cost. Okay, so one of the nice things about this particular problem, y'all, is they telling us here's the height of a can, here's the radius. So I'm just going to draw a very simple picture of my can. Right? Looks pretty rough, but you kind of get the idea. Here's my radius, and there's my height, right? And we have soup, because that's what they're telling me we got here. Okay, so a couple of things we know. We know the formula for the volume of a can is pi r squared h. Okay. The other thing we knew from the very first step is that the volume needs to be 550 cubic centimeters. So that pi r squared h needs to be equal to 550. Okay. Y'all, this problem is similar in the way that we're going to solve it like the way we did the previous problem. What we're going to do is we're going to solve this equation here for the letter h, okay? So if I solve it for h, I'm going to divide by pi and r squared, and I'm going to tell you why I'm doing that in a second. But I'm going to end up with h equals 550 over pi and r squared. The reason why I want to do that is if we're going to find the surface area, right? So we're going to find the surface area. The surface area is going to be what's the area of the top and the bottom of the can, and then what's the area of the side of the can, right? Okay, so we have two tops and bottoms, right? So if this is R, we know the area of the top and the bottom is pi r squared, but how many tops and bottoms do we have? We have 2, right? So surface area is going to be 2 pi r squared, okay? And the area of the side is 2 pi rh. What we're going to do now, y'all, we're going to rewrite this formula for the surface area only in terms of the letter R. I want you to notice, at the very beginning, we solved this equation here for the letter H so that we can now plug it in here, and all we have is the letter R. Okay. Surface area is going to be 2 pi r squared H plus 2 pi r times 550 over pi r squared. Okay. Can anybody tell me on the second part of our equation, what's going to cancel out here? Yeah, so the pi's are going to go away, and this r will definitely cancel with that one right there. So what do I need to do with the 2 and the 550? Multiply. Anybody know anybody got a calculator? What's 2 times 550? 1,100. Thank you very much. 1,100 over an r. Okay. There's my formula for the surface area. Okay. So we got our formula for the surface area. Now that I've done that, y'all, I'm going to scroll back up here because I want you to think about what the problem was asking me to do. Let me do this so if you're still looking at it, you can see everything. It says the material for the sides of the can are 0.04 cents per square centimeter. The material for the top and the bottom is 0.05 cents per square centimeter. So we want to find the dimensions that are going to minimize the cost. Okay, what I want to do now is I want to find an equation for how much this is going to cost me. Okay, so look, I'm going to call the function C now. Remember, this was the top and the bottom. For the top and the bottom, it cost me how much? 0.05 cents, right? So I'm going to take 0.05 times the area of the top and the bottom. Okay. For the side, y'all, it cost us 0.04 cents. So I'm going to take the number 0.04 times the side, which happened to be that 1,100 over an R. Okay. All right, so let's go ahead and do some multiplying here. Let me grab my calculator. Let me turn it on, clear it out. 0.05 times 2, should this be 0.1? Yeah, so this is a 0.1 with a pi and an r squared. 0.04 times 1,100 should be maybe 44. There we go. 44 with an r. Okay. So this equation here, y'all, is telling me how much it's going to cost to make that can. Okay. The reason why I wanted to find that equation is because we're trying to minimize the cost. Okay. So we're trying to minimize the cost. The way we're going to figure that out is we're going to find the derivative of it. Okay.
So
0.2 pi r, right? Pi is just a constant, y'all. It's just like if the number there was a 7 or something like that. You're just multiplying the numbers out. And 0.2 times 1 is 0.2 times pi is still pi with an r. Okay, y'all, can I think of this r right here as what? R to the negative 1. So do we end up with a negative 44 over r squared? Good. Guys, doesn't this look very similar to the problem we did earlier? Right? In the sense that we're having that r to the power 2 on the bottom, right? We had the same thing in the other one. We had an x to the power 2 on the bottom. Okay, now the way we're going to find our critical values, y'all, we're going to take this derivative and we're going to set it equal to what? There you go, 0, my hero. So that means 0.2 pi r is equal to 44 over r squared. Okay. Remember what we did before, y'all? Thought about that over 1, and we cross multiplied. So that's going to give me a 0.2 pi r to the third equals 44. To solve for r to the third, I'm going to divide everything by 0.2 pi. And then to find r, we're going to take 44 over 2 pi. And on my calculator, y'all, to the power of 1/3, right? So let's do this. Let me clear this out. I'm going to put parentheses 44 divided by 0.2 with a pi. And actually, I probably need to do it this way. 44 divided by 0.2 with a pi. Okay. And all of that is being raised to the power 1/3, right? And the number that I'm coming up with, y'all, is 4.122 if I go to 3 decimal places. Anybody else coming up with the same number? Yeah. I'm sorry? We good? Jennifer, am I doing okay? Did I lose you? Anybody? Guys, are we all good here? Just checking with y'all. Just want to make sure we're good. Okay, so look, y'all, we found the value of r, right? Okay, so look, I'm going to scroll back one more time over here. Come back to my original problem. Okay, now again, y'all, I haven't yet verified this, but again, if I wanted to verify this, I want you to think about what I would do. This, we took the first derivative, right? To verify that this is actually going to be a minimum, what we could do is we could say, look, let's take the second derivative. If I took the derivative of this, that would just be a 0.2 pi. If I thought about this right here as an r to the negative 2, that would be a positive 88 over r to the third, right? That's what my second derivative would look like. I want you to think about this for a second, y'all. Isn't this number here positive? Because it's 0.2 pi, right? So there's no negatives there, and pi is about 3.14. So that number is positive. If I plugged in 4.122 and I raised it to the third power, that just means it's 4.122 times 4.12, right? A third. And I divided it into 88. I don't know what the number would be, but I know it's still going to be positive because I'm taking a positive number divided by another positive number. So a positive plus a positive is still greater than 0. That's going to be my minimum. Uh-huh. So yeah, look, so if this is to a negative 2, when I multiply it by the negative 44, doesn't it become a positive 88? You see what I mean? Yeah. 4.122? Probably. Do it like this, John. John, look up there on my calculator. Enter it in that way. Better? Oh, okay. Okay, there you go. Oh, okay. So look, y'all, so there's my value of r. So look, we're going to come back over here. What's the radius of the can? We came up with 4.122. This is in centimeters, right? Okay. Look at the second part, y'all. It says, can we find the height of the can? Didn't we solve for the height from the very beginning? The height was equal to 550 divided by pi r squared. So look, I'm going to go like this. 550 divided by pi times 4.122 squared. And that's exactly, guys, on my calculator, the way I'm going to enter this in is like that. Okay. So look, I'm going to go 550 divided by parentheses pi and 4.122 squared and another parenthesis right there. And I'm coming up with 10.304. Okay.
Yeah.
Right? 10.304. Okay. All righty. Almost done, y'all. Last step. Last step says, what was the minimum cost? Okay, so look, if this, oops, if this equation right here was the cost, can I just plug in those numbers now? Can I just plug in those numbers for R into here and I can find that minimum cost? Right? So look, I'm going to come back over here, y'all. I'm going to go back to the old school and say, look, that's really over R. So I'm going to do it this way. I'm going to say, let me clear this out. 0.1 times pi, R squared. So R squared was 4.122 squared, okay, plus 44 divided by 4.122, close it off, and here is my minimum cost. So is anybody else coming up with 16.01? Yes, 44 over R. $4.122, something like that? Yeah. So when I did this, y'all, I came up with 16.01. You forgot the square? There you go. Okay. So we got our answer and we found that minimum cost. Okay. So y'all, a couple of things I really wanted to kind of emphasize here. In both this problem here and the problem that we did before, I want y'all to notice something. The first thing we did is we used the volume formula to solve for like the letter Y here. We used the volume formula here to solve for the letter H because we're trying to write the area in terms of only using one letter. So because this was a can, we wrote the area only in terms of the radius. Because this was a box, we wrote the area only using the variable x. Okay, so what I'm trying to show you is there's like a little bit of a pattern. Start off with the volume, solve it for the height, right? The height here happened to be y, so we solved it for y. We solved it for the height here, which was actually h, right? H for the height. And then we go with the surface area, and then we can do whatever it is we need to do, okay? So y'all, that wraps up 4.7. Let me do this. Let me go ahead and stop recording. Let's see, let me come back over here. Stop recording.